Hello, welcome to Computer Science 142, Design and Analysis of Algorithms. Our first chapter is about mathematical foundations. Here, we'll discuss the basic knowledge that we need in order to start analyzing algorithms. Some of these topics have been already discussed in lower computer science subjects, and some have not. Regardless, we will assume that you are still knowledgeable on the algorithms and data structures discussed to you before. So let's start. What is an algorithm? By now, you should be able to answer this question. You could say that it's a step-by-step procedure done in order to solve a problem. Another definition is the following. An algorithm is a well-defined procedure used to solve a well-defined computational problem. A well-defined computation problem usually has a set of inputs to be transformed to a set of outputs. Analysis of algorithms. Let's define what that means. The analysis of algorithms is the theoretical study of computer program performance and resource usage. In programming, what is more important than performance? So when you create software, what are some things that you value more? Think about this. Let's say that you have taken a project in Computer Science 128. You created software. What are those things that are more important to you than performance? You might value correctness. It's better to be more accurate than fast. How about maintainability? Maybe it's better to be easier supported in the future than having a fast software. Same goes for stability, or maybe extra features. Another good one is security. Obviously, secure software is much more important than having being fast for, let's say, banking or email. Another good one is user friendliness. Some would want to have a more user friendly interface than having a super fast one. If that's the case, why study algorithms and performance? If there are things that are more important, why study them? So why study algorithms and performance? Often, performance measures the line between the feasible and infeasible. That is, if it's not fast enough, it's not functional. Or if it uses too much memory, it won't work. You can think of performance as money, in which you can pay for other things. So performance is the backbone for all things we do. Let's say that your program is already very fast. Maybe you could add some features to it, even if it slows it a bit down. Studying algorithms and performance also gives us a language for talking about program behavior. Identifying the different behaviors of algorithms will let us know which ones are better than others. So this is why we study algorithms and performance. Now, before we actually study, let's review some methods of proof. So how do we prove which theorems are true? The first one is proof by mathematical induction. This will be our main way to prove. Let's specify the steps. We have 3 steps, sometimes only 2 depending on the resource you're looking at. Regardless, it's the same thing. Step 1 is proving the base case. We prove that it works for small numbers. Step 2 is assuming an inductive hypothesis. This means that the theorem is assumed to be true for all cases up to some value k. In step 3, we prove that the theorem is true for the next value. This is your inductive step. Let's have an example. Theorem. Show that n squared minus n is divisible by 2 whenever n is a positive integer. First, we have to prove that this theorem works for the base case. So let's prove it using the smallest possible numbers, in this case, the smallest positive integers. Let's start with 1. Substituting n with 1 will give us 1 minus 1. So if we substitute n with 1, so that's 1 squared minus 1, we'll get 1 minus 1, which is 0, and that's divisible by 2. Next, substituting n with 2 will give us 2 squared minus 2, so that's 4 minus 2, which is 2, and that's also divisible by 2. Substituting n with 3 this time will give us 3 squared minus 3, that's 6, and that's also divisible by 2. With that, let's say that it works for the base cases. If it became false for any of these tests, then outright we say that the theorem is false, and we'll no longer go to the other steps. Step 2. Inductive hypothesis. We assume that it's true for any number k, so assume that p of k is equal to k squared minus k, and that's divisible by 2. Now we prove that it works for the next number, k plus 1. So prove that p of k plus 1 is equal to the quantity k plus 1 squared minus k plus 1. And we prove that this whole thing here is divisible by 2. So let's prove. Let's first simplify this term here, k plus 1 quantity squared. So we'll get k squared plus 2k plus 1. And then let's simplify this term also. So distribute the negative symbol, minus k minus 1. And let's simplify some terms, but let's not fully simplify this whole term here. So we'll get k squared minus k plus 2k. Again, we did not fully simplify this whole term here. We intentionally created this, I guess, expression. K squared minus k plus 2k. Now, why did we do this? And what can we do here? Notice that if we separate the terms, k squared minus k, let's look at it individually. Okay? And then 2k. So let's separate these terms, this term and this term. Now, if we look at k squared minus k, we actually saw this before. Where did we see this term, k squared minus k? This is our inductive hypothesis. We assume that k squared minus k is divisible by 2. So, going back here, we now know that this term here, k squared minus k, is divisible by 2. And 2k is obviously also divisible by 2. How's that? How is that so? How did we know that this is divisible by 2? Well, obviously because we have a factor of 2 in our term, 2k. So since k squared minus k is divisible by 2, it's an even number. And 2k is also an even number. Adding two even numbers will result into another even number. So since k squared is even, and 2k is also even, p of k plus 1 is also even. Even number plus even number. So we have just proven that our theorem is true. So some tips. Tip number 1, use base cases to be familiar with the problem, pattern of equations, expressions, and other relationships. And the second tip is to use the inductive hypothesis in proving the inductive step. Okay, now try this. Show by mathematical induction that 5 raised to n minus 1 is divisible by 4 for all positive integers. So do it on your own, and then I'll post a video expressing the answer, showing the answer. Okay?